So in general, when we are talking about quantization, we are migrating from real space or complex space into Hilbert space. The difference between these two types of space is the dimension of those space. Hilbert space is a larger space that allows us to define infinite dimensions compared to like simple vectors in the 3D. When we are taking it to the Hilbert space, we're basically talking about infinite dimension space. And when we are talking about classical variables or classical observables, we are talking about a number or one number. But when we are talking about Hilbert space, we are talking about operators, and operators are collection of numbers. So any operator corresponds to a collection of eigenvalues and eigenstates, and that's how we think about them as something that has multiple numbers inside of them compared to classical variables. So a classic example of it is x and p. So when we are talking about a single particle, we are talking about location and momentum as variables. They can be also vectors. So I put this arrow on top of them to show that they are like vectors. But when we are talking about operators or operator vectors, doesn't make a difference. You can have a vector that the component of it is operator. Then we quantize them. And a very good signature of Hilbert space is that we can define those commutation relationship between those observables. So now I can basically drop the h bar and put everything equal to 1. So h bar, c, the speed of light, are equal to 1. And this is called the algebra that define the relationship between those variables. And we're going to see how this algebra is effective when defining the dimensionality of the Hilbert space. And when we are talking about Hilbert space, we have to distinguish between the Hilbert space of the states. So the Hilbert space of states, or something that we can show it on a bracket, and then the operators, or also together they form a Hilbert space, and also the vectors, or they form their own Hilbert space. So we can define these two Hilbert spaces, and they are related to each other, but the way that they are connected, that the vectors are affected by operators and operators can change the vectors, that allows us to define those quantum mechanical operations. So the whole quantum mechanic is to separate the vectors from the Hilbert space, while in classical physics we only have one vector space, and that vector space is just simply showing us the variable that we are talking about. For example, the x location or p, they are just simple vectors in real or complex spaces, but there is nothing above it. There is nothing to change them. So they are always one variable that we can keep track of them. But when we are moving into the operator and vector notation of quantum mechanics and their dual spaces, we are expanding or algebra that we can perform into something more complex that it can satisfy what we need in order to get a quantum mechanical friendly formulation. Okay, now we start from a simple harmonic oscillator. So in classical physics, simple harmonic oscillator is some massive object that is connected to a spring, and this massive object has a mass m, and we model the spring force with some constant k that is just simply a constant to model the hardness or softness of those springs. But the whole point is that the simple harmonic oscillator might be seen as a spring and a massive object connected to it oscillating, but in fact it is a potential. So we can say the potential that correspond to simple harmonic oscillator is something like kx squared, and this is the first term or the lowest order term that we can expand any complicated potential. So if we think about the potential might not be as simple as kx squared, it can be expanded into the first order term into the kx squared. So in that sense, the simple harmonic oscillator is the simplest approximation of any potential, and it does a good job in modeling the oscillation back and forth of location and the momentum of the particle. So it's a very useful idea in classical physics, but when it comes to quantum mechanics, it becomes very useful because it provides us the basis to see how we can quantize the field. So the whole idea was that any simple harmonic oscillator has a Hamiltonian. The Hamiltonian is written as omega squared x squared plus p squared. Another way to model this simple harmonic equation is the equation of motion. So equation of motion is already decoded into the Hamiltonian, but by using Euler-Lagrange equation, we can extract the equation of motion from Hamiltonian or Lagrangian. But simply x double dot plus omega square x is equal to 0. That's the equation of motion for simple harmonic oscillator, and anytime we see something like that, we think about it as the mathematics of simple harmonic oscillator. And this kind of math is already figured out, and we know the solution, how to solve it, and we can then use it to even quantize the field. But now we are just not dealing with the equation of motion. Let's think about the Hamiltonian, and now we quantize the Hamiltonian. We just basically try to turn the Hamiltonian into operators. So it's omega squared, x operator squared, and p squared operator. And we are still talking about a single particle, simple massive particle. We're just trying to convert a single particle into quantum mechanic formulation, and we already talked about it in the first video that this kind of view is not useful in the atomic and subatomic physics, because we are not dealing with single particle. But when we say single particle into the quantum mechanic framework, it can be useful in certain approximation. For example, in the hydrogen atom, it can be useful. But at a certain point, we realize that there is no such a particle. Particles can annihilate and be created, and then when we are dealing with that type of particle production and annihilation, we need to migrate into the field formulation. So we basically define a field. That field is defined in extensive points of space, and then those particles that are produced by those fields, they can migrate from point to point, but at the same time the field can create multiple particles. So we are not just dealing with one distinguishable particles. There are indistinguishable particles that could be created and annihilated. But now we're just going to see how this formulation of simple harmonic oscillator can explain certain way that we diagonalize the energy. So the question is, now I define this Hamiltonian, and these Hamiltonians are the operator Hilbert space, and then we have the vectors, and the vectors are usually defined in a basis. So a vector can be explained in terms of x basis. So when x operator acts on the x vector, it is giving us x, but we can also put this vector above those states. It doesn't really matter. I'm talking about one-dimensional or three-dimensional vectors. What really matters is that when the x operator acts on those certain states, the outcome is this eigenvalue. And similar to p, the p operator acts on the state p, and the state p comes out as the outcome. So these states are not really useful for us because x and p, they commute with each other, and we cannot really find at the same time two eigenvalues of x and p. So it's not really useful to talk about those bases. We should talk about energy bases. So we are talking about energy bases. The energy bases are the Hamiltonian eigenvalues and eigenstates. So the energy or the Hamiltonian operator acts on the energy states n, but I don't really want to show it with n right now because we still don't know if it is integer or it's a continuous even state, because x and p are continuous. So if we are living in an interval from 0 to L, any point in between can correspond to a state x, x prime, x, these primes are only trying to distinguish between these points. But the whole point is that the dimension of this space is uncountable. It is not countable. It is continuous, and it's infinite dimension Hilbert space. We are talking about infinite dimension Hilbert space. But now when we are going to energy states, we're going to see energy is more well behaved. So we're going to have some ground state energy, and then the other states of energy are just integer jump in that ground state energy. So Hamiltonian is something, for example, that when we're acting on energy states E, it is giving us state EE. So the coefficient is the eigenvalue, and then this is the eigenstates. So that's the basis that we are interested. And the question is again, what are the eigenvalues of energy operator? So what are the eigenvalues of energy operator? And the mathematical trick to do this diagonalization, that question leads into diagonalization. Diagonalization means we're trying to find out those eigenvalues of energy, or basically if we think about the Hamiltonian operator, and if you try to imagine if that operator corresponds to a matrix, so these are not equivalent, but there is a certain mapping between any operator to some form of matrix. We are trying to find those elements that live by the diagonal axes of this operator. So the rest of them are zero, and it's a very interesting argument in the linear algebra that if you have Hermitian operator, you can diagonalize them, and there is a systematic way to diagonalizing those operators. And the diagonalization of the energy operator means we're finding out what are those eigenvalues of the energy. So for the case of simple harmonic oscillator, I think it is done first by Werner Heisenberg, is to do a mathematical trick. So we define some extra operators that we really don't think that they are observables. So the operators, we talked about it, they correspond to observables, Hermitian operators. But there are some operators that are not like observables, so they do not correspond to something like location or momentum, but they can create and annihilate states. So they are called creation and annihilation states. So the operator x can be written as 1 over 2 omega, and the reason is to write 1 over 2 omega is for conventional reason, in order to cancel out when we are writing a Hamiltonian. But we are basically free to choose any coefficient. But the whole important algebra is that we write x as the summation of two operators, a plus a dagger, and the first one, the a, is the annihilation operator, and a dagger is the creation operator when they are acting on a state. And the p, if we define p or momentum operator as I, the complex number, times 2 omega, the omega was the characteristic frequency of the system, as the subtraction of a minus a dagger. And now if we define x and p, then the Hamiltonian can be written as h bar omega a dagger a plus plus 1 over 2 I operator. And then I have to also mention that the algebra between a dagger and a is similar to the algebra of the x and p. So it is equal to IH bar I. Or I mean, we can take out IH bar as we talked about it. But it's not that bad. So IH bar is emphasizing on the quantum mechanical nature of those observables. But a dagger and a do not commute, which means creation and annihilation cannot happen at the same time, very similar to measurement of location and the momentum. So when we define this algebra, this is something that we define that leads us into the algebra of x and p. So then x and p will have similar algebra. So when we are talking about the Hamiltonian operator, we are also talking about the energy basis. So what is the lowest energy basis? The lowest energy basis is the ground state. So we try to show it with a notation of some zero inside of the bracket, and this zero doesn't mean zero energy, but that means that's the lowest possible energy. We cannot go any further than that. So how does it work is that when a dagger acts n times on the energy, we're going to have some state n with some normalization factor. But we can define normalization factor in a systematic way. When A acts on 0, or the energy, the vector of the ground state energy, that would give us 0. And that 0 is the actual 0. So it's null. So it's null, it's nothing. So realize that when we are expressing a Hamiltonian as a dagger A plus 1 over 2, we have some ground state energy. We call them E0. And E0 is 1 over 2 h bar omega, that it is coming from this part of the Hamiltonian. And the green part of the Hamiltonian is responsible for in which integer space we are. So E0 is E0, or the vacuum state. And then when a dagger acts on 0, we are in the state 1. 2 times it would be a state 2, 3. And it's like a ladder. And the coefficient behind it is h bar omega. So this jump is h bar omega. So we are going from E0 to E1, E2. And if you know about how Einstein solved photoelectric effect, these h bar omega are just particles, but they are added in the integer value. So that's integer nature of quantum mechanics is coming from these equal intervals of the energy state. So when you're in the vacuum and then it goes to the first energy state, you're just adding certain coefficient of some base energy. And that base energy is the particle characteristic energy, because here the frequency is simply k over m times h bar. So in the single particle term, we are just simply showing that those energy states have these integer differences. And another way to say that is the Hamiltonian is written in the way of h bar omega, a dagger A plus 1 over 2 I. So for example, when I act a state n here, let's say h bar acting on a state n, this n goes to first part, and this operator we can write it as n. So first, the A acts on N. It takes it one unit down, and then A dagger just bring it up. But by bring it up, the normalization constant, which is important here, is coming back. So the normalization constant is chosen to be, so when we are acting A dagger, A acting on N, state N, we would like to get N. So A dagger and A should have something about canceling out each other, but in the way that only leaves N in the way. So A dagger acting on, let me find it. Yes, A dagger acting on, so A and A dagger should be symmetric on the definition. So when I have A dagger acts on N, I should get N plus 1 factorial N plus 1. And A acts on N, it should give me 1 over N minus 1 factorial N minus 1. That is like a kind of symmetry between them. And then A dagger, A acts on N, it would give me A dagger 1 over N minus 1 factorial N minus 1. And then A dagger acts on N minus 1, it gives me N factorial N minus 1 factorial N. And then N factorial and N minus 1 factorial would be N. So that's how I can get Hamiltonian as a summation of h bar omega N operator plus h bar omega over 2I. So then if Hamiltonian acts on the vacuum states, the vacuum states acting on the number operator, this is the number operator, would be 0. So it would be 0 plus h bar omega over 2. So the unitary operator also leaves the vacuum as vacuum. So that's the energy correspond to the vacuum E0. And now for the other states, we would have this number operator taking the n out. So simply the procedure for quantization of the simple harmonic oscillator is just giving us this picture that if we have this potential ux, which is 1 over 2 kx squared, we would have this ground state energy, and then we would have this equal distances of h bar omega between the energy states. So the whole point is that the simple harmonic oscillator cannot go to the zero energy. It cannot go to here. So that's a zero energy. We can't have it in quantum mechanics. So we start from this ground state energy. And that ground state energy can be thinking, we can think about it as something that keeps the hydrogen atom stable. We cannot go to the zero state energy. There is always something that the quantum mechanical entity is vibrating on top of that. But something that you can ask is that what really determines the dimensionality of the Hilbert space, or how let me ask this question. So we say x and p are location for the simple particle with the state x and p. They're defining a Hilbert space which the dimension of Hilbert space for both of them is infinite, but they are not countable, or they're continuous. But when we are talking about energy states, we are talking about, again, the dimensions. It is infinite because you can have infinite energy states. So the number of the bases that you can find for the energy is infinite, but the point is that they are countable. They are countable. And then you might ask yourself, why is it like that? How did I get something countable from two uncountable thing? And the reason is the algebra between the Hamiltonian and the x and p. So when we are thinking about the Hamiltonian, as a function of p and x, if we're just thinking about a free particle, then we don't have the x term. So this x term is something that keeps the particle constrained. But when you're talking about a free particle, we are just talking about p squared. And we are familiar with the concept of degeneracy. So the whole point is that if I have py, px, and pz, and if I have some p, so I'm defining a kind of a sphere, and the energy is p squared, and we know the area of this sphere is proportional to p squared. But the whole point is that the energy degeneracy raises with the momentum magnitude. So if I increase the momentum magnitude, the degeneracy of the energy goes up, and that's how the energy is regulated. So if we are just increasing the number of the momentum of the particle, then the number of possible states of the momentum that have the same energy goes up, because the area of those sphere goes up. For the case of, for example, let's say a spin, this might be a little different from the energy. So the Hamiltonian is regulated by x squared and p squared, and that's how we can think about those infinities in the x and p converge into something countable, but still infinite, but countable and integer based. But when you're thinking about a spin, maybe that's a little bit different, but again, we're going to see how the algebra makes this dimensionality work. So when we're talking about a spin, we are talking about basically classical spin here, not going into the spin in the quantum field theory. So in the classical spin, any particle can have a spin up and a spin down. But you might ask, where did you take it from? Who said particles can only have two state of spin? I mean, we can have different state of spin, but the whole point is, experimentally, first we saw in the Stern-Gerlach experiment that if you have this particle sending into a non-uniform magnetic field that has a gradient, then the outcome only is two state. So first, experimentally, we saw, okay, there is not a continuous spin for the particle, because if we had continuous spin, we would have a continuous line of the particle that are hitting those detectors here. Imagine if I have the detectors. So, for macroscopic physics, if you have some macroscopic spin, and if you send it through non-uniform magnetic field, you probably see a uniform line. Your detector just show all the possible spin. But it's interesting, the technology at the early 20th century was enough, so we go to the very, very small particles, such as, I don't know it was exactly what type of atoms, that was probably silver or rubidium, something heavy. So they have some heavy atoms at that time, and that heavy atoms had one electron in the outer shell. That electron, so basically all the electrons inside were canceling out each other, so the behavior of the atom was not governed by those inside electrons, but that outside electron might have a spin up and a spin down. And when you're putting these atoms into this non-uniform magnetic field, the Stern-Gerlach experiment just saw there are two states, and that was the surprise. That was the first quantum mechanical observation in terms of experimental view. But the experimental is not, the experiment is not the reason we think why the spin should have finite dimension. The algebra of the spin is something that determines what is the dimensionality of the spin. So in general, when we are talking about the spin operators, we're talking about Sx, Sy, and Sz, and then the S squared, or the magnitude of a spin, is defined as Sx squared plus Sy squared plus sz squared. And the algebra now between sx and sy is something like IH bar, some Levi-Civita symbol of x, y, and z, sz. It's basically just to rotate those x, sx to sy to sz back again to sx. And if we go clockwise and counterclockwise, this symbol is just taking care of +1 or -1 cases. So the whole point is that we, in the spin sector, we realize, okay, we cannot measure the spin of the particle in the different axes at the same time. So sx and sy and sz cannot be measured at the same time. But we realize now we can measure s squared and sz at the same time. So if we just simply write s and do this algebra, I mean, this relationship is directly coming from this commutation relationship. This is a fundamental commutation relationship. And when you go from here to here, then we realize that's a good news for us, that we can measure the magnitude of the spin and one of the component of the spin. So that allows us to define the state L and M. So there's a state L and M. Those M and L are two different eigenvalues. One of them is for sz and the other one is for s squared. So when we have s squared act on L and M, you would get L squared, L and M. And when we have sz act on L and M, we get M, L, and M. But what is the relationship between L and M? Is that M is always between plus L and minus L. Well, let's say the s squared is a larger space and the sz is a smaller space, because s squared consists of sz, but there is an algebra between them. So sz and s has a commutation relationship. One of them is a subset of the other one, and the dimension of that subset is something sandwiched between the dimension of s squared. So I mean, there is no limit how much L can be. L can be 0, so that's a spinless particle. L can be, for the case of L equal to 1/2, M can be between 1/2 and -1/2. And the jump between those states can be +1 or -1. I mean, there is no, the jumps are, the steps and the jumps are integer, that's +1. So that's again quantum nature. But the end point and the start point determine how many states we have. So we have only, for example, if you define it at 1/2 and -1/2, you can only have 2 states, jump from here to there. For the case of L equal to +1, then this dimension goes up. So M can be 0. So L can be between, let's say, +1 and -1. But we are not only have 2 states, we can have +1, 0, and -1. Now the dimension of sz is 3. And for the case of L equal to 3/2, this dimension goes up. So I just want to show that how the dimension of L can determine the dimension of sz. And that's how the dimension of a space is determined by the fundamental algebra that exists between those two operators. Okay, so I think we really discussed about simple harmonic oscillator enough, and now it's time to go to QFT, exactly, go to the Klein-Gordon field and see how we can use this knowledge from simple harmonic oscillator that we realize, just talk about the spin, but basically about the dimension of the Hilbert space and these energy states that we have, those energy states that we have, and how we can use similar way to quantize the field. So the mathematics is similar, but the field is just an extensive object defined on space and time. So For this case of single particle, again, we were talking about x and p as observables. So these are like physical location and physical momentum. When we are talking about a field, so the field itself is the observable. So the field is x, but it is defined as the space. So this x is a grid, or it is a label. It's a coordinate. It is not something physical. It is a way that we label the space-time. So we label different x. So this is the way we grid, and we can change it. So the whole point is that if I change it, rotate it, it shouldn't really change the physics. So the whole point is that the phi is the physical location, and that x inside is the coordinate or the grid. And when we are talking about, again, the momentum space is the same. So these are not the momentum, the physical momentum. So the physical momentum of the field, as we talked about it in the Noether's theorem. So we have this phi of x. This is like physical location of the field. So if phi is large, it means more particles. If phi is small or zero, it means no particle. X is the grid, and then we define this conjugate momentum, pi of x. So that's a physical momentum. So when we are talking about pi of x, the pi is the physical momentum, or the observable momentum. Again, x is the grid, and now I can define everything based on the momentum space. So I'm talking about some phi tilde in p space, or in the grid of momentum coordinates, and then pi tilde of pi. So we need to really distinguish what's the difference. So when we are migrating into from x and p, x goes to phi, p goes to pi, but both of them can be defined in x, or they can be defined in p. But we are going to the p, to the momentum coordination, because we are going to try to define momentum basis, and we are trying to quantize the momentum, the energy states based on the momentum basis. So the Hamiltonian is defined as phi dot squared plus the gradient phi squared plus phi squared. The Lagrangian can be seen as phi dot squared plus delta phi squared minus phi squared. But we just try to look at the Hamiltonian. So the Hamiltonian is similar to the simple harmonic oscillator. It is some x squared, similar to x squared, and this part corresponds to the momentum squared, or the derivative of the observable squared. So we know we have time derivatives and we have a space derivative, and time and space are similar, but they only have this Lorentzian signature. Okay. And when we are talking about equation of motion of the field, so we talk about equation of motion of the simple harmonic oscillator. The equation of motion for Klein-Gordon field is box squared plus m squared of phi of x is equal to 0. And this is for uniform. So this is for uniform, or just a simple case that there is no external current. So you can have box squared plus m squared acting on phi squared is equal to some j squared. And this is the non-uniform of, there is some source that is coupled to the field that we are using. So to quantize the second version, we need another formalism, more advanced formalism. It's called path integral. It is similar to what we do in thermodynamic partition functions, but we are not talking about it at this point. We are just gonna see how we're gonna quantize a uniform Klein-Gordon field. So if we are just looking at the Klein-Gordon equation, it doesn't look like a simple harmonic oscillator, because in simple harmonic oscillator you only had the second derivative with respect to time plus some frequency and the variable. So you have only the time variable plus the variable itself is equal to 0. But we know box squared is the time derivative minus the space derivative. So it is not still in the form of simple harmonic oscillator. So the reason that we migrate from a space grid to momentum grid is to define the equation of motion very similar to simple harmonic oscillator. So for example, I say if I have phi of x, that's why I do the Fourier transformation, because I want to show it to you that that's a Fourier component of the field which acts like a simple harmonic oscillator, and that's the momentum grid. So phi of x, you can say phi x of t. Now I can distinguish between space and time, and let's do that. But we can basically define phi of x, but x is just a 4 vector, so it can be having x0 and then you can have x as a vector. But if we think about phi of x and t is the summation of d3p, now the space component of the momentum, divided by sum 2 pi cube, which is more for conventional term. And then you have this phi tilde of p and t. Now I'm talking about p and t, so again I separated the time here, but I'm gonna show it to you that t and energy now are gonna be the same things times some exponential term which connects p and x. This is the Fourier transformation, and in the Fourier transformation you want to find this coefficient. In the classical physics you're talking about Fourier transformation. But if I now try to think, okay, I have this Klein-Gordon equation, box squared plus m squared acting on phi of x is equal to 0. Now instead of phi of x, I put the Fourier transformation of it. So I have, let's say, box squared. Now I'm trying to write box in terms of space and time. The space minus x variables plus m squared acting on the integral of the integral over momentum cube phi tilde of p and t, and then exponential of ip dot x is equal to 0. So it's because integral is a linear operator, I can just take this integral into back and then try to write this equation phi tilde of p and t exponential of p dot x, and then I have this differential element out of it is equal to 0. Now something interesting. So the first term can act on phi tilde. So I would have the time derivative of phi tilde p and t. But now this time derivative doesn't act on exponential of p and x. And that's why I separated time and space, because if I didn't separate it that, I might have this problem with that. But now if we are thinking that p and x are only a space component, then this phi of t can act on only the Fourier component of it. So I'm writing down this Fourier component. Let me write it with the white color. So I have this phi tilde of p and t, and instead of the time derivative symbol, I would just write down double dot. So this is double dot that we were thinking about it in the simple harmonic oscillator. And then now the space component, and this is the problem, the space component doesn't make the Klein-Gordon equation to exactly look like the simple harmonic oscillator when we are writing it in a space coordinate. So that's why we need to go to momentum coordinate. So if we go to momentum coordinate, now this space derivative cannot act on this phi tilde, and it only acts on exponential term. So when it acts on the exponential term, what comes out is the momentum. So we're going to have I squared plus. So I have minus, so there's a minus sign here. And then I have I squared p squared, so that comes out from the exponential term, phi tilde of p and t, and then this exponential term I'm trying to factor it out. And the next term is just m squared times phi tilde of p and t, and then I have this exponential term out times the differential element of the momentum space is equal to 0. And now that's the beauty of it. So the beauty of it is that we can ignore these two terms, the differential term, because it's an integral equation, and just put the expression inside of the integral equal to 0. So I would have phi tilde of p and t so double derivative plus, so now I squared is minus 1, minus with minus is plus, so I have p squared plus m squared of phi tilde of p and t equal to 0. And that's a simple harmonic oscillator. So the Fourier component of it acts like a simple harmonic oscillator, and that is the frequency, the characteristic frequency. So the characteristic frequency, omega squared, and I can add the index of p to it now because it's a function of p. P is the variable, it's a grid that we define or system on. Is defined as p squared plus m squared. And that could be seen as energy. We're going to later see that's basically energy. So energy squared is equal to p squared plus m squared. And what does it tell us? That's the relativistic energy dispersion. So that's very beautiful. We can think about it as Klein-Gordon field creates each particle, and when it creates a particle with the momentum p and the energy of p squared plus m squared, that characteristic frequency of the simple harmonic oscillator is just basically the energy of the particle. So the energy of the particle is similar to the frequency of the particle, and the whole quantum mechanics starting argument on how energy and frequency are related can be answered here. So for a case of the photon, the energy and frequency are, there was no mass term. If you have a massive term here, where you cannot really talk about it in just relativistic terms, because photon, you can write, for example, the energy of photons completely proportional to energy and momentum. And so energy of the photon, for the case of photon, E was equal to P with some constant. But the whole point is that energy and momentum can be attributed to each other as the same entity. But now if you have this m squared term, you have some mass term, now the energy can be defined as p squared plus m squared. But the way that those fields oscillate is that the energy is the same as frequency. So we would write it as, for example, in the case of simple harmonic oscillator, we were writing 1 over 2 omega a plus a dagger. So this is the way that we express for the single particle case a plus a dagger, and p the same as I 2 omega a minus a dagger, right? Now we are just trying to define the analogous version. So we are trying to write down the analogous version of those particles. So we can write down, so x and p, x were the one who were satisfying the simple harmonic oscillators. We had x double dot plus omega squared x is equal to 0. Now we have this phi tilde of p and t now can be written as 1 over 2. So now I have this omega here. So there was no characteristic, x didn't have any functionality. It wasn't a function of anything. It was just one variable. But now this phi tilde is a function of p. I should have this index p down here, and then I can have again a plus a dagger, but then I have this index p. So now I'm talking about creation of a particle with momentum p and an annihilation of the particle with momentum p with the characteristic frequency of p squared plus m squared. So it depends on the mass of the particle. And in the same manner, you can write pi tilde of p and t as similar to momentum. I 2 omega p a plus a dagger of p. I'm going to put this index with the magenta color, so to make clear that now we are just migrating into something more that has more numbers inside of it, but similar algebra, similar math, similar way to express it. Now I have this phi tilde. Phi tilde is acting like a simple harmonic oscillator. The phi of x now is the integral over 2 pi 3. And just remember, we are still in the classical space. We didn't turn them into, we are basically, let's just say, the operator phi of x is simply can be written as 2 omega p a dagger p exponential of I p dot x plus a dagger p exponential minus I p dot x. If I replace the phi tilde inside. And now, what's the interpretation of that? So when I act phi of x acting on the vacuum, I just simply saying that I have this integral d3p of 2 pi cube 1 over. Now instead of omega p, I just write it down as energy p. And that energy is the same energy that we saw in relativity. So EP is equal to p squared plus m squared. Now I have this term, AP exponential of I p dot x. So these exponential terms, they came from the definition of the Fourier transformation. So you have two independent modes for the Fourier transformation, plus or minus, so they are independent. So one of them acts on AP and the other one acts on a dagger p. And then you have a dagger p exponential of a minus p dot x. So now these are all acting on the vacuum state. So vacuum states goes to a operator, and that turns into null, 0. Then vacuum states goes to a TP, a dagger p, and the outcome is simply, so we have the exponential dp 2p 2 pi cube 1 over energy states, and then I have exponential of minus e pi dot x. Then I have a dagger of p acting on the vacuum. So that's interesting to see how, in the case of simple harmonic oscillator, we said if a dagger acts on state 0, that would give us state 1, right? So if a dagger of p acts on state 0, that would give us a state 1 of p. So that means we are creating one particle with the momentum p. So a dagger creates a particle with the momentum p, one particle. So we are creating particle. So this is the recipe to create a particle out of vacuum with this. So and then phi of x acting on the vacuum means that we are summing up over all the possible momentum. So we can create a particle but with the all possible momentum. So I can create any momentum I want. You probably saw some of those Feynman diagrams that you have nothing and then you create a particle and then you annihilate the particle. So that basically means you create something out of vacuum and then you annihilate that particle from the vacuum. That's the processes that we can just simply do. But if we're just thinking about it as a visual picture, phi of x creates a particle with momentum p. And then you create Hamiltonian out of those. And then you create a Hamiltonian out of those phi. And then you create a Hamiltonian out of those phi of x. And this Hamiltonian is a function, the functional from phi. It's a function of some other function. But the whole point is that the dynamic is exponential of Hamiltonian. That could be expressed in terms of, if you do Taylor expansion of that, you can notice Hamiltonian can be expressed of terms, and each of those terms are basically phi squared, consists of phi squared, phi cube, and those terms. So a Hamiltonian, which can be seen as the dynamics of the system, is just simple creation and annihilation of particle in a complicated way. So something as the motion of the particle. So imagine if you have a field, if you have a space, and if you have a field, so you can just simply say the propagation of the particle can be seen as continuous creation and annihilation in certain point. So you just create a particle, annihilate it, and then you create and in another point or in another direction. So those Hamiltonians can encode the motion in all direction, the motion of the particle, but not in the classical manner. So this is not a particle going from one point to another point. That's a whole field, but the field can pop some particle out and then unpop it and then pop it from another point in a consistent manner. And now I can just simply write down the momentum, conjugate momentum operators as the integral of d of p 2 pi cube minus I, and the energy term on top. And then you have AP exponential of I pi dot x minus a dagger p exponential of minus I p dot x. And now again, the fundamental algebraic commutation relationship between a dagger and a dagger p prime. So the reason I put p and p prime is to show that now we can talk about two different momentums. That would be I h bar delta of p minus p prime. So you can create and destroy two particles with the different momentum. That would be 0. So if p is not equal to p prime, then that commutation relationship would be 0. So you can't really you can separate if you have two particles with two different momentums. But if p is equal to p prime, then your delta function is not 0. So that's where your uncertainty comes in. For one particular momentum, you have the restriction to create and annihilate, and then the fundamental relationship can lead into the concept of phi x and pi of y. Now I'm going to space, because again, this a dagger and AP don't have a space component, but phi x and pi, they are integration over the momentum to create a space component. But with a very, very simple algebra, if you know how these delta functions are defined as an integral of exponentials, you can just simply show that this is equal to delta of x minus y. Because if you just do the algebra and then you integrate it over all the momentum, then you're going to get this delta function of a space and time out of it. So the Hamiltonian can be expressed as now the integral over all possible momentum 2 pi cube a dagger p AP plus 1 over 2 the commutator algebra of AP and a dagger p, which can be seen as again the unitary operator. But now we are going to see what's the difference between the simple harmonic oscillator and the field is that now we have this integral. So when we are now, let's see what's the energy of vacuum. So for the case of simple harmonic oscillator, the energy of the vacuum state was, so the energy of vacuum state. So when we are acting the Hamiltonian operator, let's say, if I'm acting Hamiltonian operator on vacuum, I get h bar omega 0. That's the finite vacuum state that I have. But now let's do it for the case of a vacuum for the field. So now I'm just acting this Hamiltonian even at one point. So now one point that you can call it x. So you have to remember, I'm defining a Hamiltonian operator as a function of x, a space in time. But if I want to calculate all the energy, now I have to sum all the energy. So I can also integrate the Hamiltonian over d3 of x, right? And then thinking about the whole energy. But now I'm not going to integrate over all x. I'm just trying to integrate over just the p, the fact that we can have all the momentum, possible momentum. So h of x now acting on 0. So I want to see if I have the vacuum state and now the Hamiltonian at some point, the Hamiltonian operator at some point, what is the energy at one particular point that is coming from the vacuum state? So we basically again have this 2 pi over 3. Now I can just write a dagger and ap as np, or the number operator, plus 1 over 2 of vacuum. So the first term is just 0 because vacuum doesn't have anything. So this is 0. But the other term is equal to the integral 2 pi cube. So the other term is like that. So what is the result of this number? This is infinity. So that might be a little strange. You think about how this energy is infinite. The ground state energy is infinite. That's equal to infinity. And that is coming, that would be another argument. That's a very deep argument. The vacuum energy becomes infinite. So we basically have infinite energy, and then we are building up our universe on top of that. So that's the energy of the field configuration. If you think about similar argument in electrostatic, so in electrostatic, let's say you have a finite dimensional charge. So let's say I have an object, and then I have the rho of x, or some electrical charge density on top of that, and then I try to integrate it. The energy of this configuration is finite. But now I'm trying to make a singular point. So if I just try to take this finite volume and take it into a point, and then you try to calculate the self-energy of this system, this is equal to infinity. And why? Because again, the whole point argument, to bring everything into one point, you need infinite energy. And the whole idea that if you define a QFD vacuum, each point of it has infinite energy. But the whole point is that we don't really care about that energy, because energy is always we are talking about energy difference. So we can always jump on top of energy and ignore that energy, and then we try to add the energy that it is coming after that. So the vacuum energy is a concept that we can talk about it later, maybe in the greater depth. But that can have a very interesting application in cosmology. In cosmology, you have different energies. For example, you have energy in cosmology. If you think about the whole universe, if you think this is the whole universe, this universe can have several components. It can have matter, or fermionic system, and you can have radiation, and you can have the vacuum energy of vacuum. And that energy of vacuum has a different behavior from energy or matter. The way that they diffuse as the universe expands. So as the universe expands, the matter and radiation energy, they would scale with the factor 1 over 4 and 1 over 3, but the vacuum energy is constant. Vacuum energy is always constant, and that can drive into the accelerating expansion of the universe. And there is some certain connection, not certain actually, there is some possible connection between a concept of a vacuum energy and what probably we see in cosmology. There is a connection between cosmology and QFD at that point. Another question is that how do we define the inner product P and Q? So I mean, we said we are talking about the occupation number representation. So when I'm acting a dagger P on the vacuum, I get as one particle P state. And if I have, for example, a dagger P acting 2, I would get 2 of P states. If I have a dagger P prime, a dagger P, I would have one particle of P and then one particle of P prime state. So we can just try to show them as P and Q. So I mean, I'm just dropping this number 1 or 2. I'm just writing it as P or Q or P and Q. So when I'm talking about that, each of those P and Q represent one particle with that characteristic energy. So we're gonna show how to define Q and P inner product to define well-behaved integral. But first question is that why do we need that? Well, we need that because we need to understand what's the inner product of those bases. So these are our bases. And then now the question is how to define the inner product of them. How to define the inner product between Q and P. So to define that, I have to reproduce a one particle single wave function. So in the first quantization, so this the whole procedure here is called second quantization. Second quantization is something related to the number, the occupied number representation. But let's forget about those terms, first and second quantization. You have this single particle that we talk about, let's say single particle harmonic oscillator or single free particle. But now I'm just talking about single free particle. If you remember it from quantum mechanics, then you have the box with the scale L, and then you have one single particle inside of it, and then in the Schrödinger equation of that box would lead into the concept of psi of x. Psi was wave function, so psi of x is a wave function. Wave function for what? For one single particle. And that's, the psi squared of x was proportional to the probability of finding a particle at certain x. So at certain point, we're trying to see what's the probability of finding a particle. So remember, wave function is not the same as quantum field. So wave function is only defined for one particle, and it's a classical field. So psi of x is a classical field, and that represents probability of finding another particle. So now the question is how to basically define one single particle, how to create one particle with quantum field theory, and try to see if their momentum is equal to P. So I create one particle. This is how I do it. So the phi of x, or the Klein-Gordon field acting on vacuum, this creates a particle. And now I try to project that particle to have the momentum P. So that's again one state particle. One particle with momentum P. And now I want to see if this one equals to psi of x. This is equal to psi of x, or a single particle wave function. So to do that, so I can just, for the matter of simplicity, I can just, the whole point is that it doesn't make a difference if I write it as P acting on psi of x, but it can do both of them. So simply we try to first express how can I create this state P, and that's the whole point. I brought the P to the right side because I want to show that I want to write P in terms of a dagger of P acting on state 0. Because we just seem familiar with the concept of a dagger acting on the bracket on the right side, but everything is the same for the dual space. But now we are just, for the matter of being more convenient, we brought P on that side so I can write it like that. So now I try to calculate this term. So the state vacuum is the vacuum. Oh, something fundamental that we studied is that vacuum is equal to 1. So that's how we define the basis inner product, at least to the vacuum state. So vacuum is 0. Now the question of how to define P and Q, or on the other hand that I'm trying to write, yes, P and Q is good, not P and P prime. P and Q. Now I define a state vacuum as vacuum, and then I define the whole psi of x. So I'm trying to write vacuum phi of x acting on a state P, and then I would write it as vacuum, the integral over some other variable. I choose Q. The reason I choose Q is that P is another variable, so if I want to bring it into an integral, I cannot use the same thing. 2 over 2 EQ. And then I have A Q E Q dot x plus A dagger Q E minus E Q dot x acting on a state P. So I would write a state P as A dagger P acting on vacuum, but there need to be a normalization constant. So probable normalization constant to reproduce the same wave function of the single particle, and that is the concept of 2e pi. So I need to put this normalization constant beside that to create a proper coefficient to cancel out these energy states, and that's why I'm gonna show that this is gonna affect the concept of inner product between the two states P and Q. This is coming from the fact that if I want to make a proper Lorentz invariant inner product, the inner product that doesn't change with the boost, I need to define a Lorentz invariant operation. So when I'm acting the vacuum, the state vacuum on the A dagger of P, I need to put this energy proportionality beside that. So as the result, the outcome of the inner product is Lorentz invariant, because those energies are gonna cancel out each other. And then if we boost the system, we are not changing the outcome of the inner product. So we need to create a Lorentz invariant volume or Lorentz invariant inner product. So now if I define this already normalized relationship between the A dagger acting on a vacuum, giving us some proportionality with the energy, now I can have this state vacuum acting on. So the first term here, let me write it down, d3q 2 pi cube. Now I have this energy 2eq term. So I have this aq exponential of iq dot x plus A dagger q exponential of I minus q dot x. Now I have this A dagger P acting on vacuum, and now it's like inverse of that, so I should take the energy up. So I have 2 EP square root. So let me just bring it inside. So I have 2 EP A dagger P acts on vacuum. So that's the beauty of it. So this energy is going to cancel out this energy when we are integrating, and that's how we're going to get some Lorentz invariant factor, something that doesn't depend on the energy scale, because we need to get rid of those energies. So now the first term, so again, so this vacuum comes to the first term, that's 0. Good. So I have vacuum. So let me take the integral out. So I take the integral out, d3q 2 pi 3. So I take this integral out, and then I have vacuum. Oh, let me also take this energy out. So we have EP, EQ, those two cancels out. And then now I'm taking vacuum. Then I have A dagger Q, A dagger P. So now how to calculate this expression? I would take the integral and those elements out. 2 pi cube, square root of EP, EQ. Now what do I have? I would have vacuum AQ, A dagger P, plus vacuum, those exponential term also. So I should put this exponential term E IQ dot X, IQ plus, I have this second term here. So vacuum between A dagger Q and A dagger P of the vacuum. So now how to calculate this expression. So I'm gonna use the fundamental algebra between those states. So now how to calculate this expression. So this term is 0. I can just simply show, because when we are having two of the same type of the creation or annihilation operator, when we are having two of them, that's always 0, because one of them, so it depends which of them in what dual space is that, but here this term is equal to 0, so that makes it null. Now the question is how to calculate the first term, and that's it. So now I get rid of these, so I only remain with the first term. So this is something that we don't know how to calculate it, but we can use some beautiful, so our goal is to calculate what is the expectation value of some AQ, A dagger P acting on the vacuum. Let me write AQ, A dagger P as the commutation of AQ and AP, A dagger P, plus, now plus what? So if we are expressing that, the first term is the first term, but the second term can be seen as A dagger P AQ, right? So now I'm just writing it as the commutation of AQ and A dagger P vacuum plus A dagger P AQ acting on vacuum. And it's a happy time because this is equal to 0. So the whole second term is equal to 0. And now I just remain with the first term, and I know the first term. The first term is IH bar, or let's get rid of H bar, I delta of Q minus P. So now I just know how to, and then vacuum on vacuum is equal to 1. So the outcome is something that we can calculate now. So I have d3q 2 pi 3, and then I have this energy EQ, EP, and then this part, magenta part, turns into I delta of Q minus P exponential of I P, q dot x. And I'm just I can just basically take this I also out. This is a conventional term. Doesn't really make a change. But now I can integrate over all q. So I integrate over all q, and then I have a delta of q minus p. So I'm replacing all the q with p. So the energy term becomes 1. Sorry, and there is also this factor 2 pi 3 in this commutation relationship. So I just want to get rid of this 2 pi over 3 because this is just a coefficient. It doesn't really change anything, or it doesn't depend on energy, momentum, or anything like that. So when I put this 2 pi cube here, I can also get rid of this 2 pi cube. So what I remain with that is the exponential of I p dot x. And that is the wave function of a particle with momentum p in the space. So that's how I created one particle and projected into some momentum space to create a single particle. And to obtain that, I define the proper normalization factor here that would give us a Lorentz invariant answer that doesn't depend on what frame of reference we have. Now, if I change the frame of reference, this outcome is just affected by the momentum, not something by the energy, because we already have these energy terms here. So we basically wanted to get rid of this energy in order to create a Lorentz invariant result. Okay, now we are at the end of this session. I think we covered enough about quantization. So that's how we are just making a one-by-one relationship between the simple harmonic oscillator quantization and the Klein-Gordon field quantization. And in the next session, we are going to talk about other types of field, Dirac field and Dirac algebra. But this is how basically a field quantization works. It is not something very complicated. It is not something very weird. It is just it is just an advanced form of simple harmonic oscillator quantization. And that's how we can think about particles as a set of creation and annihilation operator. And now we can also expand it into many body systems. The system that doesn't only have one particle, it can have multiple particles in the momentum space. So in the next session, we're going to talk about Dirac field and then how to quantize the Dirac algebra. Thank you so much.